This is part 4 of the series Relationships Within Triangles, and we're going to start this part with the midsegment theorem. Now, a midsegment of a triangle is simply a segment that connects the midpoints of two sides of a triangle. So in this triangle, DE is connecting the midpoints of AB and BC. And the midsegment theorem tells us that the midsegment of a triangle is parallel to the third side of the triangle, and its length is 1/2 the length of the third side. So DE is going to be parallel to AC, indicated by these little arrowheads, and the length of DE is 1/2 the length of AC. Now, this theorem is fairly straightforward to prove if you use a coordinate proof, but it gets a little bit more complicated when you don't use the advantages of a coordinate proof. So if you wish to go ahead and prove this, coordinate proof is going to be the way to go. Now, you might be able to see the elements of the proof here. If you notice, triangle DEB is a dilation of triangle ACB. It's a smaller triangle, but you can see that this angle is the same as angle ABC, and so it shares that angle. This side is half the length of AB, and BE is half the length of CB. And so you can see then that since this angle is the same, that angle is congruent, and DB is proportional to AB, and EB is proportional to BC, that these two triangles, the small one here and the big one, are similar triangles. And their scale factor is going to be a scale factor of 2. That is, every side in triangle DBE would be multiplied by 2 to get to ABC. So that's a very grotesque outline of the proof that you're dealing with here, but you could go through a more formal one if you'd like, but it's not part of the lesson that we're going to go through here. What we want to do is go ahead and use the midsegment theorem to solve some more practical problems. So let's go ahead and do that. In this problem, they're telling us that MN is the midsegment of triangle JKL. So MN is a midsegment, not the midsegment. And we want to find out that MN is parallel to JL. So we're dealing with slopes here. So the first thing we need is we need the coordinates of M and N. So point M has coordinates -4, 3. So we're at -4 and 3. And N looks like 0, 2. So N is 0, 2. And J and L have coordinates that are given to us. So let's find the slope of MN. So it's the difference of the y's, 3 minus 2 over -4 minus 0, which is 1 over -4. So -1/4 is the slope of this one. The slope of JL is the difference of the y's, so it's 1 minus -1 over -6 minus 2, which is 2 over -8, which is -1/4. So the slopes are the same, so yes, in fact, these two are parallel. Now, to find that this is 1/2 this, which is what we're looking for here, we need distance formula. So we're going to take these 2 points and find our distance. So -4, 3, 0, 2. -4 minus 0 is -4. 3 minus 2, 1. Square, add square root. Remember our SAS principle for distance formula. And that's 16 plus 1. So it's the square root of 17. Okay, let's do the same thing for JL. So we have -6 and 1, 2, and negative 1. Negative 6 minus 2 is negative 8. 1 minus negative 1 is 2. Square, add square root. 64 plus 4 is the square root of 68. Now if we simplify this radical, 2 goes into 68, 34, 2 goes in 17. So these are our prime factors, and so that's the same as 2 square roots of 17. All right, and so because this is half of that, in other words, this is twice that, clearly this piece, this segment, MN, which is square root of 17, is 1/2 JL, which is 2 square roots of 17. All right, let's move on to another example. So in this example, we have a roof truss, and we're told that UV and VW are mid-segments of this triangle, and we need to find the length of UV, this length, and RS, which is going to be this whole length up here. Well, because these are mid-segments, we know if this is 57, RS has to be twice that. So we know then that SR, or RS, has to be 57 times 2, which is 114. And since RT is 90 and UV is a mid-segment, this piece has to be half this piece. So we know that UV equals 45, or 90 divided by 2. So once you get the idea of the mid-segments down, these examples are really pretty trivial to execute. So now let's move on to the next section. In this section, we're dealing with two related theorems. The first one is the triangle longer side theorem, and it says if one side of a triangle is longer than the other side, then the angle opposite the longer side is larger than the angle opposite the shortest side. So it's kind of an obvious statement. If this side is longer than this side, then this angle is going to have to be larger because it has to open further to include that side than this angle has to include this side. So longer side, largest angle, smallest side, smallest angle. This is the triangle larger angle theorem. It's basically the converse, if you will. If one angle of a triangle is larger than another angle, in this case this angle, then the side opposite the larger angle, is longer than the side opposite the smaller angle. So big angle, big side, big angle. Small angle, small side, small angle. It's kind of a statement of the obvious. The proof, on the other hand, isn't quite so obvious. So in our picture here, we're given that the length of BC is greater than the length of AB. And we're told that these two are congruent. We want to prove that the measure of angle BAC, the angle opposite, this BAC is opposite this longer side, is greater than the angle opposite the smaller side. So given a longer side, we're trying to prove that the angle opposite the longer side is larger than the angle opposite the smaller side. So to begin, we're going to have to relate angle BAC to angle C. So we can say the measure of angle BAC equals the measure of angle 1 plus the measure of angle 3. This is the angle addition postulate. Now looking at angle C, we know that angle C is related to angle 2 and angle 3 because angle 2 equals angle 3 plus angle C. That's the exterior angle theorem. So we know that the measure of angle 2 equals the measure of angle 3 plus the measure of angle C. So this is the exterior angle theorem. Now to write all these together, we can see that this is an isosceles triangle, and therefore angle 1 and angle 2 are the same. So you know that angle 1 is congruent to angle 2, and that's the base angles theorem. And therefore the measure of angle 1 equals the measure of angle 2, and that's definition of congruent angles. Now that takes care of the most obvious facts, but what we have to do is we have to show that BAC is somehow greater than angle C. Well, we see here from this expression, because you have to add something to angle 1 to get to BAC, we know that BAC is greater than angle 1. And so we can say that the measure of angle BAC is greater than the measure of angle 1, and that's basically the definition of addition. And we see here that angle C is less than angle 2, but since angle 1 equals angle 2, we can replace the angle 2 here with angle 1. So let's use substitution there and say that the measure of angle 1 equals the measure of angle 3 plus the measure of angle C. And this is substitution. And because you have to subtract something from angle 1 to get it to equal angle 3 or angle C, you know that the measure of angle C has to be less than the measure of angle 1. So this is definition of subtraction. So because BAC is greater than angle 1 and angle 1 is greater than angle C, then by the transitive property you can see that the measure of angle BAC is going to be greater than the measure of angle C. So the measure of angle BAC is greater than the measure of angle C. Okay, well that's a form of the proof. There are probably many ways that we can solve the same proof, but this one will work. And so now let's move on to the next section.